I guess what I'm trying to say is, I remember teaching microscopes, but I always started out the lesson this way. I'd say, I know a lot of you think you know how to use a microscope, and you're convinced yourself you do. And I said, I already know which ones those peoples are. What they do is they first get the microscope out, and what they do is they put their finger on it, and they go like this with a coarse adjustment knob. I said, that tells me right away that how little you know about how to use a microscope. The only reason I say that is that even though I wanted you to discover something, when we did the Circle Lab, it's not like I didn't think you knew what pi was. That wasn't it at all. It's to say, could you discover maybe where they originally got the idea of pi, and they did it with graphing. And this one right here, it's not like I don't know that you know what trigonometry is. It's not that at all. But did you discover something? And that was the idea. So I think sometimes there's a little bit of pride or arrogance that, after you figured out, well, everybody in the world knows this was sine or cosine, and that's what it is, so that's what it is. But that wasn't the point. The point was for you to discover something. So let's see, let me ask you this question, okay? So you have these triangles, and they're all 30, 60, 90 right triangles. And you got a whole bunch of them, and this right here is the adjacent leg, and here's the opposite, and here's the hypotenuse. All right, so what happened when you did this graph? When you were doing your measurements, you eventually had a column of adjacent leg and an opposite leg and hypotenuse, but then you had these ratios. And so all I wanted to do was, I'm gonna get a piece of paper here. You have your okay, so hopefully when you were doing this, I know it's hard to pretend like you were the first person to do this, but somebody was. Somebody said, I want to study triangles. I want to study the relationship. And that's what this whole unit is to interpret data, to actually do an experiment that generates data and then try to interpret it. And so what did you find out? So the first graph you had to do was this one. This one was this right here. So what happened here? Kieran, what happened in the first graph? What do you think?
It was a direct proportionality.
Okay. And did you find that your actual measurements pretty close to where the best fit line was? And that's always a good sign. If you start seeing things like this, and that's your best fit line, that means your measurement technique is pretty bad. You get that? So if I saw dots that were fairly close to the best fit line, it means your measurement technique was good. Also, then this also only has one slope. So in science, that's a constant, right? There's some kind of a constant involved here. And so hopefully in your analysis also, you have to come up with an equation. So y equals mx. So opposite equals the slope you got here times this right here. Karen, you don't happen to remember that number, do you? Okay, all right. Everybody remember the number for the slope on the first graph? What do you have? 0.577. Okay, let's take a look. Okay, and so 0.577. Now I don't know how close you got to that. Are you pretty close on yours or not?
Pretty solid, yeah.
All I was trying to do with you is to show that that's probably where this came from. But I'm not saying it's not a theoretical thing now. Just like pi is a theoretical number, and I'm sure that tangent and cosine and here's your math teacher coming, so ka do, and so I already know you had that lesson, but it's different when you have the lesson where you have to remember this and just do what they tell you. You just make sure you put the opposite over the hypotenuse, and that'll be the sign. And I know there's mechanics in math. Math has mechanics. And some of you are really good at mechanics in math. All I was asking you to do is to apply the math in here and see what was going on. So if we were to take this equation here and divide both sides by adjacent, And there was something, and again, I'm not trying to say you've never done that in math class. That wasn't my point. One thing here is that what happened when you had centimeters divided by centimeters? What happened to the units of the slope of this graph? What would the units come out to be? Yes. And in almost every case, if your units cancel in a scientific graph, it means percent. And so maybe you have not thought of it. I doubt whether any math teacher has told you that in a 30, 60, 90 right triangle, that the opposite leg is about 58% of the size of the adjacent leg. That almost never comes up. What they usually do in math is they'll simply say, they'll go like this, they'll go x, 2x, x times square root of 3. Is that right they do? And I did that. I did that for many, many years. I understand that. That was the way the math teacher did that. If I were teaching math, that's what I would do. But I was trying to get you to the point to say, hey, what does that mean, you know? I get it. Just plug it in, and the mechanics, you get it right. But what it really means is that in every 30, 60, 90 triangle ever made, that the opposite leg will be about 57.7% of the size of the other one, of the adjacent. What about the other graph? The next graph was, this was opposite over hypotenuse. And let me ask, Rollins, what kind of graph did you get for that? Okay, and do you happen to remember the slope on that one? Okay. What was it? 0.5. Okay, 0.5. So opposite equals 0.5 times hypotenuse. You know, and when I was your age, I was just told the mechanics, and that was good. And I just thought these numbers, see all these numbers here? These 3-digit numbers? They were just 3-digit numbers that you look up. And matter of fact, we didn't have calculators, so we had to look them up. Matter of fact, if they fell in between two numbers, we had to interpolate it. So if it came out between these two numbers, we had to figure out the exact angle by just using algebra. All right, now I think you put that in the calculator and it does it for you, doesn't it? So if I look here, this is the equation I get from the lab that you did. Or another way of saying it is opposite over hypotenuse equals 0.50, which equals 50%. Again, no math teacher ever told me about 0.500 meaning 50% in trigonometry. It was just, hey, what's the sine? What is this one? What's the sine of 30 degrees? Well, first of all, what do they mean? What do they mean with the sine of 30 degrees? And he said, well, it's just a sine. What do you mean? What is the sine? And it is a ratio. Yes, go ahead.
It's the ratio of the length of the opposite side of the length of the hypotenuse.
So somebody a long time ago thought it was important to find the relationship between these sides of a triangle. And then, and there's a lot of consistency, isn't there? A lot of constants here. Like, you don't say, well, how big of a 30, 69 triangle? How big? It doesn't matter. It comes out to be the same. And I doubt whether a math teacher said this to you. In a 30, 60, 90 right triangle, the opposite is always 50% of the hypotenuse. What they tend to do is say this. What do? They say the hypotenuse is what? Twice the side of the short leg. And I doubt whether that translates to you and says, well, the short leg's 50% of the hypotenuse. Matter of fact, it's the only right triangle made where this side here is half of the size of the hypotenuse. The only one. Okay, yes?
How do you think they found the relationships between them to make them come out so evenly? Did they just like play around with numbers and go lucky?
I'm not, when you say evenly, what does that mean?
Well, 2 and square root of 3 are very even numbers.
Oh. Even though, that's a great question. If you start making triangles, right, and you start here, a really flat one, and you start going like that, isn't there going to be a point where this one's going to be like half the size of that one? I mean, if you could make any angle you want, it's got to happen sometime, doesn't it? What else, though? What about... What about, so I think, I don't see any problem with having a point, but it just happened to be, why is the one that is twice as big here, why is that kind of an important one? And I think, in my opinion, here's what I think. What happens if you put, like, more than one of these together? What would you get? What if I put two of these together? What would you get? What if you put two of the, why do people think the 30, 60, 90 is important? I think number one, because of that, it's the only one that's twice, the hypotenuse is twice the size of that. When you put them together, it makes another kind of a special triangle. What's that? Equilateral. I think that's unusual. I think the 45, 45, 90 is also an important one, because what if you put two of those together? What happens there? Woo. Then you get, I don't draw that very well. Then you get like a 90-degree angle, don't you? So I think it might be a couple reasons why those are. I thought I put in a basket. Okay, thanks. So that's a great question. Why do they think those are the important triangles? That's a good question. I think it had to do with making things, building things, or what they had to do relationship with other things. I want to show you. I want to show you one more thing about this. I know that you're, again, if you had trigonometry at all, I know you've done problems like this where here's a flagpole and the sun's shining, and okay, here's your flagpole. Okay, and anyway, so how would you find the height of the flagpole without having to climb up the flagpole? How would we do that? Which one of the trig functions would you use if I want to find this guy right here? And I think something that happened to me also, even though I could do the mechanics in math, I was actually pretty good in math. I've never asked to use the math in another light necessarily. Like, very rare, this only happened later, maybe rarely like that, but how do you know which trig function to use to find that? And how would I actually do it? Let's say today I went out to a flagpole and there's sun is shining, and I said, find the height of that flagpole. What would you do? Yes, go ahead.
First you would need to find either finding the hypotenuse is going to be kind of hard, so I would find the.
That's going to be hard, yeah.
So I'd find the length that's from where you're standing to the.
Okay, so I could actually measure the shadow, couldn't I? All right, and what else can I measure?
You can measure the angle of the shadow.
Right, if I could somehow line up a stick or something to line up along the shadow, I could maybe get a measurement right here, and then I hope this is 90 degrees here. So let's say we do have that, right? Which trig function do you use? Yeah, what do you think?
What you would do, okay, so you do, so it's opposite over adjacent, so that's cosine. Oh wait, no, sorry, that's tangent.
Okay,
So
tangent is opposite over what?
adjacent.
Okay,
So you would do tangent of whatever that angle is.
let's say 60.
So tangent of 60, and then on the other side you'd say
Okay.
equals, x over the shadow length.
All right, and so again, and if I was a math teacher, I'd teach it exactly that way. I would say you're trying to solve for what? X. So you have to look up tangent of 60. And another thing that confused me a little bit, I don't think anybody ever told me what was tangent. I don't think they ever said, well, tangent is a ratio. I remember memorizing this, and I used it to do my problems, but it is the ratio. The tangent is the ratio. If I look up the tangent of 60 degrees, I see that it's 1.73. So the tangent of, what does that mean, the tangent of 60 degrees? It means in a right triangle as seen through the eyes of the 60-degree angle. What is the ratio of opposite over adjacent? That's what it really means, but it takes too long to say it, doesn't it? As seen through the eyes of the 60-degree angle. That's what they mean. The tangent of 60 is see the triangle through the eyes of the 60-degree angle and then tell me the opposite over adjacent. Because if I see the triangle through these eyes over here, then I can't use 60, I have to use 30, don't I? And if I see the triangle through the eyes of a 30-degree angle, then this is opposite and this is adjacent. And I have to think differently there. All right, so, and also, it was just a set of three numbers to me. It was just numbers, they didn't represent anything like percent or something like that. All right, I want to show you one more application here. This is a simple application about how tall it is. And I've ever done rockets, little rockets, you send rocket engines like engines. Ever done that? Have you guys made rockets? And they actually have this little thing you can buy, and it's looks like a gun, but doesn't shoot anything. But you go like this, and that's as high as your rocket went. And anyway, then they tell you how to calculate how tall your rocket was. Did you know that was trigonometry? Except a 9-year-old doesn't know trigonometry, but you can teach them to look up on a chart, can't you? And somebody else already figured out the chart. Say if you do that, that's about how high your rocket went. I want to show you one other application, though, I think is kind of neat with this thing here. Do you remember this word? Remember that right there, parallax? We were talking about measurement. And, for example, you have two eyes, and if you go like this, remember that? Okay. It's the apparent shifting of an object. I'm not actually shifting, but I went from one eye to another, and it actually can cause error. And if you're looking at a ruler, which eye is dominant? Which eye is actually taking the reading? Or if you're using a graduated cylinder, what if you're reading too high? If your eyes are too high, you'll get a parallax error. So things like parallax is a bad thing. But they, long ago, even the Greeks knew about how far the moon was from the earth. How is that possible? How is it possible they could know that? How about the sun? How could they possibly know an estimate how far the sun is? And so if we took the earth like here, and you were sitting here and I was sitting here, and we were both looking at the moon, we pretty much, compared to any reference you want, we would pretty much get the same angle if the moon, say the moon's over here. Yes?
How do you know the earth is round, not flat?
All right, that's another issue, but you could always tell me that all the pictures taken from space, including not just from astronauts but satellites, you could all say they were faked. You could say they were all faked. That's fine. And you could tell me there are no pyramids in Egypt because I've actually never been there. I might not be there. They might not be there. But you're right. It takes a certain amount of information for me to believe something. And are there things right now that every one of us believe that might be false? Yes, that's possible. I don't think this is one of them. In this case, I have seen a lot of information. So anyway, in this case, I choose to believe that we have been in space and we have had pictures, and the satellites, when they take a satellite picture of the Earth, it looks round. I'm okay with that. If the people on the moon, you say, well, I don't think they went to the moon. That's okay. That's okay. You don't have to. Yes?
How did the Greeks know the earth was round?
Okay, now, believe it or not, they thought about things. They were, here's what we tend to believe. We tend to think, well, we're in the 21st century. We're so much smarter. And look at our things, our phones and things like that. We're so much smarter than those other people. Back then, how smart could they be? Really? They did a lot of things without all the technology stuff you have and machines. They had certain machines, but not like you have. I'm always amazed at how smart they really were. Why are we still using the same geometry they came up with a long time ago? What's that all about? Well, we should have figured out new geometry. No, they figured it out, and they worked pretty well. Well, let me go back to my story here, okay? So, one thing that they knew, they had figured out long ago that when they saw an eclipse, now a lunar eclipse is when you look at the moon and you see it getting dark, all right? So lunar eclipse means it's at night, I'm going to look at the moon, and I'm going to see a roundish type of a shadow invade the moon and maybe cover the moon and come back again. They figured out a long time ago that was the Earth's shadow being cast on the moon. That was another reason they were pretty sure the Earth was round. when we talk about the Eratosthenes, and what he did with shadows, he figured out how round the Earth was, and he was within less than 5% error. That was pretty good because the Earth is slightly flattened anyway, but even from space, you wouldn't probably notice it. So to make a long story short, you think that parallax is a bad thing for measurement, but they had to use parallax to figure out how far it was to the sun or even the moon. And so if you have people that are kind of close here, they're not going to get a different angle here. You're over there and I'm in Alamance County or something like that. There's no way you're going to see a difference in an angle. I need an angle difference to make a triangle, don't I? And let's say we're both looking at the same part of the moon, and I'm just not going to get any difference here. I won't be able to measure the difference in angle. So what I need to do is I could have somebody on this side of the planet. How about somebody over here and somebody over here? That would increase it. Now, I'm way out of scale, but I can tell you right now, even that would be an incredibly, they get almost identical angles if they were measuring it. So even this wasn't big enough. This parallax, in a way, having people look at the same object from two different sites, this is one way they're going to do it. But it was even for the sun, and this way they could do it for the moon. That would work pretty well for the moon. All right. But what if this were the sun? And what they did is, I thought it was pretty smart. I'm going to have to change my scale drawing here a little bit. Here's the sun. And what they did is they would take a picture, they would take a reading, for example, they would take a reading of, and even stars, trying to figure how far stars were. If the Earth goes around the sun, then what if you could look at a star and you were here, like on June 21st, first day of summer, and you looked at this star compared to some background stars, okay? And then you waited 6 months, for the first day of winter, and then do the same thing. And so if you're wondering how were they able to actually get an angle difference great enough to make a triangle? You see that? And that's how they did it. They used all this trigonometry was used to figure out the distance from the Earth to the moon, Earth to the sun, and even an estimate of maybe how far the stars were away. And so this is actually called a parallax determination of distance like that. So parallax, again, looking at the same object, the apparent shifting of an object, which in this case they really did shift. They just waited 6 months to take their reading. I just want to show that to you because there's a lot of applications to this besides just a flagpole and stuff like that. Yes?
How would they do the actual math for that?
Okay, so let's say I see this angle here and I have this angle. Then what I would do is if I could find those two angles, I can cut this triangle in half, and there's my right triangle. So is that what you're asking about?
Well, how do they get the original distance? Because sure they have a 30-60.
This one?
Yeah, but how did they get the first side to start?
Okay, so they would have, let's say you know the circumference of the Earth and you know the diameter, right? So you know the radius of the Earth. So let's say we know the radius of the Earth and we know this angle. Now what?
But the radius is not that. You're talking about the entire solar system.
Oh, I'm sorry. I was doing the moon. My fault. When they did the moon, I was doing Earth radius. That's my fault. That's a good question. Once they found out how far away from the moon, I see what you're saying. Then they had to find out how far away from the sun, and then you're right. Then they had to know the Earth-Sun distance, and then they had to make a triangle out of that. That's a good question. If they knew the Earth-Sun distance, then could they? And that's another thing. Now, I'm not your astronomy teacher, but all the planets tend to go in ellipses. They're not really circles, but they're ellipses. So they had to know a little bit of mathematics about ellipses also. So yeah, that's a good question. I would use parallax to find the moon distance and the moon diameter, and the sun-Earth distance and the sun diameter. And then if they wanted to find a distance to a star, they would go past that. Yeah, go ahead.
So walk me through how they use parallax to find the Earth and sun distance.
One more time.
How did they find the Earth-sun distance? Let me say that one more time.
Okay, so the Earth-Sun distance would have to be, I would have to take a reading, like, for example, let's say you had some, Let's see here. Let me think about this, because here you had to be here. Somebody on this side of the planet would have to take an angle, and they'd have to have some kind of a standard. Say, what's my standard? My standard is going to be some 90-degree angle. What's my standard going to be? I'd have to do a little bit of reading to know what standard they used to determine this. I know they could figure this out, but what was the standard of angle? I have something that measures angles, and it'd be pointing at the sun from where? From here, and then somebody over here. So that's a good question about when they were finding the determination, the distance from the Earth to the sun, what were their standards? That's a good question.
No, that was the moon. How did they do it for the sun?
Well, the same thing, just like instead of looking at the moon from different parts of the Earth, I just say I can look at the sun. I could still spot an angle. I could still do an angle to the sun. Now, I would have to take my reading at the exact same time as the other person on the other side of the planet. Yes?
So on the test, would you give us the distance to the sun, or how would we do a question on the test?
Well, I'm not going to test you on this, but if I did, just like trigonometry does, if trigonometry says here's the tangent of theta, a tangent of theta equals blah blah blah, opposite over adjacent. Here's 1, 2, 3 items. I have to give you 2 of the 3 items, don't I? So if I give you 2 of the 3 items, you can solve for the other one. So I'd have to give you 2 of the 3 things here. Yes.
So when you're going from the Earth to the moon,
Uh-oh.
the moon is smaller, so you can create the point at the moon. But since the
Yes.
sun is bigger, doesn't it invert?
You would have to, for example, I would have to pick a point on the sun, and I know that maybe you've never seen the sun with filters. Have you ever seen the sun with filters? There's all kinds of sunspots and things like that, and they could pick a point on the sun and say, I want you to point your best instruments at that point at the same time. The moon, they could pick a certain crater or something like that as their point. We now have, this has been probably over 30 years ago. One of the moon missions, they went to the moon, and it was a French scientist who made a very special mirror, and they actually planted that on the moon's surface, and daily they shoot laser beams at the moon, and they whatever angle that the light comes in, this special mirror bounces it right back at you. And then all they do is they hook that up to an atomic clock, and they say, ready, go, tune, fire back. And by knowing the speed of light, and by knowing how long it took, they can actually tell within 10 centimeters, they know the exact distance from the Earth to the moon. That's pretty good. So there are a lot of things we did, and I know if you ever thought to yourself, well, I'll never use trigonometry, but other people have, and they've done great things with it. So I want to change gears a little bit here, and I'm going to give you, could you help me out and give everybody one of these, please? Are you willing to do that? This next lab, again, I think we already talked about Boyle's Law. So it's not that, I don't think the goal of this next lab is for you to learn Boyle's Law. What I'd like you to do is, though, again, if you can pretend that no one has discovered this yet, and you can say, my job is to try to figure out the proportionality that exists between these 2 variables. Now, so one of the goals is to confirm Boyle's Law, but my main goal here? My main goal is for you to start using electronic software, to start doing your data tables and your graphs and your analysis, doing that, instead of doing it by hand like you've been doing. And then what I'm going to do is I'm going to give you a final exam after Boyle's Law, and then you have the tools that you need. Then I will give you one more lab, which will be your final exam, which I just called that. But really what it is, it's where you and your team, you get to design the experiment however you want, but your goal is to solve the puzzle. What is the relationship between this and this and this and this? See that? And so one of the reasons I want you to do the Boyle's Law lab is to see the equipment we have, okay? What kind of equipment do you have available to you, and what kind of software can you use? And so if I have to give you a little more time on this because, you know, you have to learn the software, I'm okay with that. But then next week, we'll have 3 days. You'll have 3 days to do the final exam. And next week, I don't think you're on here on Monday, right? Yeah, next week you're not here on Monday. So we probably Tuesday, Wednesday, Thursday. Yes?
Are we doing this lab with partners?
Yes. Now, and also this one, only one lab report will be turned in. Now, I'm okay. I don't mind this one if you pick your own partners, but on the final exam, I am not going to let you pick your own partners. I do it on purpose. I want everybody to say, I'm a valuable member, and it doesn't matter who I end up with next week, because I know I'm a valuable member, and I know how to use the tools, and we're going to do what we have to do, regardless of who my partner is. You get that? All right, so let me show you real quickly. Now, this one, even though there's not as much design, you don't actually design this lab like you've been doing, and the last one you'll definitely design it. What we're going to do is, when we got LabQuest here, I've been here about, this is my 17th year, but even one of the very early LabQuest, this is called LabQuest 2, and we had LabQuest 1 also, but I was blown away because I know how every science teacher used to do Boyle's Law. They'd have these syringes with little corks on them, or rubber stoppers, and you would lay a book on it, and lay 2 books, and 3 books, and 4 books, and you would try to take some measurements, and then what I found out most of the time, what you do is try to convince the kids that it really was an inverse proportionality. Yet the data was never that great. It never was. This is the absolute best data I've ever seen with this instrument they have. And we have this right here is a pressure gauge, okay? It's a pressure gauge, it's a digital sensing device. And so LabQuest is, let me get this started. So when you first get your LabQuest, you turn it on, little button up here. And what happens is it usually takes, I already had this out, but it usually takes about 2 minutes for it to load. It's loading up all kinds of experiments and things. They didn't know what you want to do with it, okay? And then what's going to happen is they're going to ask you to, right now it's not doing anything, so, oops, I forgot to get a sensor out. Okay, so anyway, you're actually going to use a pressure gauge, and it's going to measure pressure. And I'll tell you what, let me see sometime. I have a thermometer here. I want to show you what it can do, though. I have a thermometer, and you can see where it's round, and it goes in like that. But please, when you get ready to pull it out, there's a little thing you have to push. There's a tab you have to push. Don't try to pull it out without pulling the tab. Okay, so now, I know it doesn't sound amazing to you that the company makes almost 90 different sensors, oxygen sensors, magnetic field sensors, and they're all electronic. And this thing has the software. It doesn't matter what I put in there, what I plug in, it knows exactly what sensor I put in there. And for you, that's nothing. You say, of course it does. Why wouldn't it? But if, by me, I know the history of all kind of interfacing. I've seen it. And this is actually amazing to me. It's amazing. Maybe not to you. So here's what I want you to do. What I want you to see is that this right here is a little window, and it's called a meter gauge, a meter window. And if you just want to measure something, you just go like that. And so if I were to, if I were to just want to measure, and I put my hand on there, you see how the temperature's going up. See that? And that's fine, because that's great. If you don't do anything to LabQuest, what it will do is default to a time-based data collecting, meaning every second. Like every second, I'm going to collect data because you didn't tell me anything else. And there's nothing wrong with that. As a matter of fact, what if I wanted to look at over here, there's a little thing called a graph. All right, and I could actually, I could start taking data with a little arrow here. and I could watch real time, and I could do a little experiment where I heat it up or cool it off. Okay, so what I'm trying to tell you is that if you want to use LabQuest for something else, maybe not just Boyle's Law, if you ever want to do this again for another lab, you know that if you don't do anything, I could either use the meter mode where I just get the readings, or the graph mode. If I have a graph mode and I start pressing this little arrow, it'll start taking data. Now I can stop taking data. I can stop taking data by pushing this again. Okay. And it will have this thing called auto scale. Auto scale means whatever data you have, I'm going to spread it out. That's one of the most tedious things about graphing, isn't it? Scaling the axis. Well, it does it for you. And so that's what happened. There's my experiment right there. And if I wanted to, I could actually go to analyze. And I might even say, what if I said curve fit? And so you're going to see different things here. And curve fit is, okay. And what it'll do is it'll say, what do you think? And it'll have all these mathematical things like direct square. And it'll be something like that. And so you can analyze it, everything that can be done on LabQuest. And the good news about this lab is it kind of tells you what to do. But what we're going to do is, you're going to have your first graph, and hopefully, here's pressure, here's volume. Hopefully you are going to get good data, and hopefully it's, whoops, my mistake. Hopefully you will not get that one. Hopefully you'll get this one right here. Got that? Well, then what? Then what I want you to do is to confirm it. They have over here, and the directions tell you about this. You're going to do a new calculated column. So instead of doing P and V, then you'll probably do another column like 1 over V. See that? So you have 3 columns. And so what would happen there is you'd have P and 1 over V, and not only would that straighten out the curve, but you can also, you can ask it to analyze it. It'll find the slope for you. It'll also give you a correlation value. Say, what's the chance of this being a pattern? And a correlation like 0.998, that's up there pretty high. You guys haven't done anything like that, have you? You haven't correlation values?
No, we know nothing about it.
Okay.
He's Jewish.
No, you know, I know, but what do you call it though? Don't you, do you call them R values? Okay, you know more about R values than I do. How about that? So what's a good R value? 0.99 what? 9? Yeah, that's good. How about 0.998? Is that all right? How about 0.98? Okay. Wait. So my goal for you is to kind of learn how to do this. Now, this is part 1. So LabQuest is one of the reasons I want to do this lab. And also it's kind of neat to have this pressure gauge thing, and it really works really well. But you have to read the directions. Now, the one thing I haven't mentioned yet, I'm going to, let's go back to, okay, let me go back here to, I don't want that. There you go. Okay, so let's say we go back to, oops, there you go. So I'm on the meter mode. So this experiment here, though, is we don't really want to do real time. And so I want to tell you this thing, if you don't do anything, it's going to do real time every second. As a matter of fact, if you want to take 1 reading a second, if you want to take 10 readings a second, if something's happening very quickly, maybe you want to do 20 readings per second. It can do that. It can also do like a time-lapse thing, 1 reading per hour. What if I wanted to measure the atmospheric pressure in this room and I knew a storm was coming? I might say take 2 readings an hour, and then I could watch the 24-hour period of time with 48 pieces of data, and I could look at it. You see that? I wouldn't want to have 5 readings per second if I was doing atmospheric pressure, because I'd be getting all kinds of little things like this, and I wouldn't actually see the pattern very well. But so what I'm going to show you is the most important thing you're going to do tomorrow is this thing called mode. And so if I don't tell it anything, it's going to do time-based. But this one is called events with entries. So let me see how they go there. So the main thing that LabQuest can do, it says, I'll take readings all the time if you want, if you don't tell me not to. I'll take readings all the time. But hopefully though, you and your partners don't skip that one sentence in there. It says, change to events with entry. Events with entry simply means when I start taking data, you're not gonna take any data until I tell you to. You get it? And what's gonna happen is you're gonna change that little syringe. You're gonna change the pressure, change the volume. The pressure is gonna change. You say, ready? I tell you to take data now, and you'll press keep. And so there's two ways of collecting data with LabQuest: time-based and events with entry. Events with entry simply means you only take data when I tell you to. So you can relax. You don't have to worry about it taking data. It's only going to take it when you want it to. So tomorrow, what I'd like you to do is you're going to start out right away. And you do have to answer these questions. There's some questions in this lab. There's a data table. I need at least one. I need one of those data tables filled out. And then you'll have to do an analysis. And the main thing I'm looking for is, we've got 1 minute. We're going to make a transition then from LabQuest to a thing called LoggerPro. Now, in these laptops right here, there is this other program called LoggerPro. Now, it would be nice. Right now, I don't have any way of going right from LabQuest to a printer. Right now, I don't have that method. I mean, that would be good. So what we end up having to do is we have to take this and put it into a program on that laptop called LoggerPro. So the reason I'm giving you enough time to do this is that you're going to have some problems. Because when you go from that to another program, you have to learn how to use that program also. Now, I'm willing to give you the time. I'm going to be walking around the whole time. I'll be helping you. But my main thing is, can you get used to LabQuest and LoggerPro? And then next week, when you have your final exam, if you want to use either one of these, if you want to use LabQuest, you can. If you want to use LoggerPro, you probably should, and you can. Everybody got that? All right, well, thank you very much. Hope you had a nice weekend. Well, I have six lab tables, and we have, well, today we only have, I guess 3 and 2. I'll have to wait until tomorrow to see who's here. See, Clayton wasn't here today, but he wasn't here last Monday either.
Do you have a protractor and a ruler so I can do the graph?
Yeah, okay, the rulers are back there. And then, do you see a blue lamp back there? There's a drawer underneath that blue lamp. Yeah, right, go straight. Yeah, there's a drawer there. That's where the protractors are.
Okay.
I hate you having to do this again. There's no way.
I've looked everywhere. I feel like it could have gotten left and then thrown away or something, but
Normally, if I would have found something like that and it had the triangles on it and measurements, I definitely would not have thrown it away. But how about your partners? Would they have them?
I didn't really work with anyone, so I just started like late.
Okay.
So.
Well, I hate it. I always hate that when you have to do it again. But it is part of the lab.
Yeah. Do you want me to go ahead and turn in my write-up? I was gonna use my data points to just make sure I was in the right ballpark for my measurements, but
Okay.
I have my write-up. I don't.
How do you? So you had your data in a data table, right?
Yeah, I had a lot.
Well, that looks nice.
And then there's
Wow.
the data tables next to it, and on that notebook
Okay.
sheet. And I had that.
Wow, that's beautiful.
So, thank you.
I already like it. And you had the equation.
Yes.
I don't know if I was boring you today. I was just trying to tell you that there's the mechanics of math, and then there's the thought of what's going on here.
That makes sense.
Wow, look at the data points. They're right on that. Wow.
Thank you.
If you could somehow just draw a quick set of triangles.
Okay.
I know, and just say, I'm not gonna. Once I see this,
Yeah.
I'll just say I know you have the triangles. So,
Okay.
But just turn in the triangles. That's
Okay.
what I'm looking for mainly, the analysis. Wow,
Okay.
it already looks good.
Thank you.
Okay.
I'll
You can take it home.
Can I take the protractor?
Yeah.
I'll bring it back.